TLN, as we call it, is a partnership of Montana, North Dakota, South Dakota, and Wyoming DOTs, along with North Dakota LTAP and the Mountain-Plains Consortium of universities. I'm going to read those universities because one of our presenter today is from one of the MPC Consortium universities. Colorado State University, North Dakota State University, South Dakota State University, University of Utah, University of Wyoming, Utah State University, University of Colorado, Denver, and the University of Denver. And as you know today, as you can see by the screen, today's presentation is on the evaluation of grouted spliced sleeve connections, reinforced precast concrete bridge piers, and that's 4 reinforced concrete bridge piers. This is the overview of a research project done by our speaker, Dr. Chris Panelides. The presenter is the only one that has the capability of projecting audio over the webinar, so please be sure to ask your questions by using the chat box at the bottom of the screen, and the instructor, Chris, will answer the questions as he sees them. So you don't need to wait for a Q&A period. So drop them in as this question comes up. This session is recorded. Should you want to review part or all of the presentation, just go to the Learning Management System at translearning.org, which is probably where you registered, and in about a week it should be available for replay. The PowerPoint presentation will also be available for download. Actually, it will be a PDF that will be available for download from the LMS, similar to what was sent to you today, the PDF anyway. Now our topic and speaker, again, the topic is research presentation of the evaluation of grouted splice sleeve connections for reinforced precast concrete bridge piers. This presentation will cover research methods and results of the Mountain-Plains Consortium MPC-392 research project on this topic. The study conducted by the University of Utah was intended to evaluate the splice sleeve connection for accelerated bridge construction. The study also verified the capacity of the splice sleeve connection for precast concrete elements such as columns connected to footings or bent caps and beams. The study evaluated lateral loads, ductility, and replacement possibilities of the columns using the SSC concept. And there will be cyclic loads were also applied to simulate seismic events. As we also said in the introduction, the Utah Transit Authority has implemented the SPC concept on a current bridge on the UTAH FrontRunner Transit project. And now I'll introduce our presenter. Dr. Chris Panelides is our presenter. Chris has been with the Department of Civil and Environmental Engineering at the University of Utah since '91, where he is currently a professor and associate chair. He received his Bachelor's of Engineering and Civil Engineering from the American University of Beirut in 1980, his master's from the University of Missouri-Rolla in 1983, and his PhD from the University of Missouri-Rolla in 1987. He was a design structural engineer in 1980 from Dar al-Handasa Consultants from 1981 to 82. He was a construction engineer with Odon and Oda Stramaten. He was an associate professor at the Department of Civil Engineering at the University of Missouri-Rolla from 88 until 91. Dr. Panelides is a member of the ACI Committee 374, Performance-Based Seismic Design of Concrete Buildings. His special interests include seismic design, evaluation, rehabilitation of reinforced concrete buildings, and bridge construction. Also interested in earthquake engineering, fiber reinforced composite materials. Now, Dr. Panelides, I'll push my stop broadcasting button, and it looks like you are already broadcasting, so you can take over at any time now. Look forward to your presentation.
Tim, thank you very much. Welcome everyone. I also want to thank Dennis Brown of TLN for facilitating this. I have to give credit to my PhD student who's actually sitting here, MJ Ameli, who's getting a PhD on this topic. And I also have to thank, in addition to MPC, the Utah Department of Transportation, New York State Department of Transportation, and Texas Department of Transportation for financial support. Let me start by saying many of you know what accelerated bridge construction is. What is attempted here is to use innovative techniques, methodologies, and materials to actually accelerate bridge construction, both for new construction as well as for replacement. And of course, reduce construction time, traffic, safety of the workers, and the safety also of the traveling public, and environmental preservation, especially if you're going over streams. These are all advantages of accelerated bridge construction. In fact, the Federal Highway Administration has the prefabricated bridge elements and systems program that you see there on the slide on the left, where some of this is old. I mean, everybody knows that you can build pre-stressed girders, and you can build piers and cap beams and connect them. And the idea is, yes, you can do all this, but can you do it in a seismic region? Now, what I'm going to present to you, the couplers, they are allowed actually by the building code even in seismic regions, but when it comes to AASHTO prohibits these connections in high seismic regions because they don't like to place these connectors in the plastic hinge zones. Now, Tim mentioned the front runner, and in the middle picture you can see here a column with actually a prefabricated column that goes inside a footing where in the footing there are these splice sleeve connectors. And this is one of the things we're studying here. We as you will see, we place the connectors in the footing, and then the bars come out. We call them field dowels, and they go and connect inside the footing with grout. This here is a pre-grouted operation. You can see these little white things. These are the ports for the grout. But in addition to this, of course, there is other systems. For example, Washington has been using these socket connectors at the bottom of the column, and I will talk a little briefly about them a little bit later. And then they use grouted ducts at the top of the column. This also can accelerate construction in seismic regions. So the connectors we're going to talk about are called emulative ABC connections because they try to emulate the situation in a cast-in-place bridge, like this bridge bent with 3 columns. And of course, they've already been implemented, as I said, in non-seismic areas. But we decided to focus on this in this study on these 2 areas. First is the column to cap beam subassembly that you see up here at the top, and then secondly at the column to footing subassembly that you see on the bottom of the screen. So just a brief introduction here. Common emulative connections that try to emulate cast-in-place construction are these grouted duct connections. Matsumoto, Sacramento studied this. You can see over here the big duct in 2009, and then Tazarv et al. Studied it at Reno. You can see now it's the same thing where you have individual grouted galvanized duct. These are corrugated, and then you place the bars inside. Pocket connections are another type. Here is a column to cap beam connection, which comes from the NCHRP report 698. And I talked about this earlier, Kalegi et al. At Washington DOT. Here is a column to footing connection with the socket. This socket, as you can see, is roughened concrete and is placed inside the footing. And on the top is just a grouted duct connection. There have been some recent studies of more ambitious connections, ABC connections. These are called hybrid because they involve pre-tensioning of pre-stressing strands inside the connections with high performance fiber reinforced concrete shell at the bottom and the top. And you can see that in this case the concern, and then there is a cast-in-place diaphragm at the top. The concern here is not so much the seismic only, but it goes a step further, and it's to make it self-centering. So the concern here is not just to survive, but once you survive the earthquake, can the column come back into vertical and the bridge be able to be put in service immediately. So that's a step higher, and it's kind of in the research arena. Other research efforts in this direction include advanced materials like shape memory alloys, and this was studied by Tazarb et al. At Reno in 2014. Many of you know what shape memory alloys is, and I see here I have a message to use a larger screen. Okay, if I do that, then of course I'm going to lose my chat options. So I'm going to stay at this screen unless somebody tells me that I need to make it bigger. But here is the shape memory alloy bars at the column end. The advantage of these bars is that they are actually they have memory, and when they are heated they tend to return to their original position. The disadvantage is these are very, very expensive. So coming back to the topic of our discussion here, these are the grouted splice sleeve connections, and you see the graphic there that was produced in the NCHRP 698 report. Basically, you have a column that has bars that come down, and inside the bars are there these bar couplers or sleeves, and the bars from the footing come up and fit inside the sleeves. These are steel sleeves. I'll show you a picture in just a second. And at the bottom of the column you have a grout bed. So with this kind of construction sequence, you can end up with an accelerated construction method. These sleeves or bar couplers are also called mechanical rebar splices, and in this particular case they're called grout-filled steel sleeves. So what you need, the components in this construction are the rebar, the sleeve, and the grout. And the grout is a very high strength grout that's provided typically by the manufacturer. Now these grouted splice sleeves are inside design codes currently, mainly the Precast Concrete Committee Report ACI 550, which talks about both type 1 and type 2 connectors. Type 1 means that the rebar is supposed to reach 125% of the yield strength, and type 2 is supposed to reach 100% of the ultimate strength. ASHTO also has a full mechanical connection provision, as well as Caltrans for service and ultimate couplers. So here is a collection of different types of couplers provided by Haber et al. 2015. These can be used as a replacement for welded and lap splices. They have a considerably reduced dowel length because of the confinement and the grout provided by the steel of the coupler. They are suitable for precasting, and they have very good construction tolerance. But as I mentioned earlier, ASHTO does not permit them in the plastic hinge zone of bridge piers in seismic regions. So the two types that we're going to focus on are the first one. It's a type of a hybrid grouted sleeve, and you can see one bar at the top here is threaded. It has a tapered thread that threads onto this cast steel coupler, and then at the bottom you have another bar, and the bar is grouted. You can see on the bottom here you have a grout inlet, and on the top of the sleeve you have a grout outlet. So this is one of the types of connectors that we have used. And the second one is the grouted sleeve, and the grouted sleeve, as you can see, is longer, and both bars in this case are grouted. So again, we have a grout inlet on the bottom and a grout outlet on the top, and this is the sequence of grouting to get rid of any air bubbles. And you can see in the middle right here there is a bar stop. So previous research on these couplers does exist. For a long time, the only research was done in Japan, but they were limited. The researchers studied only strength properties, and these were typical couplers for buildings. As you can see here, a couple of different options: traditional shear reinforcing method, and also something called an intensive shear reinforcing method, where you provide ties only above and below the couplers, because in any case the couplers have steel iron cast sleeves that are very, very strong. A lot of the research was done actually for horizontal connection of bars in beams in buildings. Until recently, in 2013, Haber et al. At the University of Nevada, Reno, have studied 2 half-scale specimens of the grouted splice sleeve. You can see here the bottom where you have the inlet, and in the top you have the outlet, and you can see the couplers are inside the column end actually. In this case, 11 of them for number 8 bars. 2 options were studied. There was no pedestal in the footing. As you can see, number 1, and number 2, there was a 12-inch pedestal in the footing. So our research objective here at the University of Utah was to evaluate seismic performance of precast bridge piers with these grouted couplers or splice sleeves inside or outside the column plastic hinge. And the reason we chose to put it outside the column plastic hinge is obvious, because AASHTO does not allow it, but we also wanted to know if we do use it inside the plastic hinge, the column plastic hinge, what is the comparison. So on the left hand side here you can see the Lenton interlock. This is the hybrid coupler. This is the splice sleeve that we term here for ease of nomenclature FGSS. The F stands for fastened. As you can see here on the top, you have a threaded end where you fasten one of the bars. This is the green bar, is called the factory dowel. Dowel is the threaded bar that is actually prepared in the precast yard. And on the bottom you see the field dowel. This could be, for example, the bar coming from the column. And again, you can notice the inlet and the outlet for this particular FGSS splice sleeve, which is the Lenton interlock in this case. So one of the bars, then the field dowel is grouted, and then the other, the factory dowel, is threaded. We chose to use this particular splice sleeve for connection in column cap beam or column to pier connections, and this other one that I'm going to show here on the right, we call this the GGSS, so grouted splice sleeve, because both the field dowel, the blue one, and the factory dowel in the precast yard, the green one, are grouted. So this is taller, as you can see. They are both, this provided by the NMB splice sleeve of USA, of America, and they are both used in number 8 bars. So we use number 8 bars in both cases. So again, to go back to the original bridge bend, I'm going to now use another category to separate the two. So as you can see, the column to pier cap specimens or sub-assemblies that we used, or column to cap beams, we will call them category 1. So category 1 means column to pier cap or cap beam, and those are using the fastened grouted splice sleeve, the FGSS, that I described earlier, as shown in this picture. So for category 2, the column to footing connection, we are using the grouted or to grouted splice sleeve, or GGSS. I know there's a lot of letters to remember here, but just to distinguish that in all of the tests that we have done for the footings, we use these grouted to grouted sleeves, and for the pier caps we use the fastened to grouted sleeves. So let's start with the category 1. This is the column to pier cap connection with the Lenton interlock. And as I mentioned earlier, we put this both in the cap beam for one specimen and in the column for another specimen, just to see the comparison. In addition, we also did connector tests. Sometimes these are called air tests. And you can see here a picture of a connector test where we apply a monotonic tensile load in an instrument type machine to measure, the properties of the connector with two bars. You can see here is the bottom bar and here is the top bar. You can also here perhaps see the fastened end, and here is the grouted end. We carried out, I believe, 6 tests, monotonic tests, and in all the situations we had what you can see here on the right, what we would call a pull-out failure. In other words, we formed a cone in the grout and the bar pull out, but of course before it did that, it went to 1.44 times the average yield strength. So that's the average strength of the bar, which of course is more than 125%, which according to the ACI building code and all the other evaluations, it actually qualifies. But if you look at for type 1, which means not intense high seismic regions. But as I mentioned earlier, none of these bars fractured. And so what that means, it is a full mechanical connection, but only qualifies as a type 1 type of splice. In none of these tests did the bar fracture. And here I have the test data, which for all of them you can see the failure mode was bar pull out. And you can see the maximum load in this column, the maximum bar stress, and the ratio of the stress to the yield. So here I'm showing a little graphic of our test specimens, our sub-assemblies. These were half-scale experiments. I will show you the specimen sizes in just a second. But just to distinguish here what tests were done, the first test is an FGSS1, that's the category 1 again. But in this case, the cap beam is shown upside down because for testing purposes it's easier to put the beam on the floor, or a strong floor, and then apply load to the other end of the column. So FGSS1 shows that the splice sleeves were located in the column, as you can see here, in the plastic hinge zone. By comparison, FGSS2, you can see the sleeves are located inside the cap beam. Again, this is upside down. And both of these are precast, so that the cap beam is precast, the column is precast at the factory, and we connect them at the lab. And the last specimen has the initial CIP, which means cast in place, and this one was actually constructed monolithically. There is no precasting here, nothing was precast. This is how you would go about casting a specimen, monolithically. for comparison. And so the comparison is going to be, what if you cast the sleeves in the column, what if you cast them in the cap beam, and what if you don't have any sleeves at all. So here are the dimensions of the half-scale experiments. The particular design began with the cast-in-place specimen, of course, which was designed according to AASHTO guide specifications. In this particular case, you can see that there are lots of closed hoops inside the joint region, number 4, I believe, and the column has 6 number 8 bars. I will show the cross-section shortly. It's a 21-inch octagonal column with 6 number 8 bars, and it has a number 4 spiral of 2.5 inches. The cap beam itself has number 4 closed hoops at 2.5 inches. The width of the cap beam was 2 feet, as you can see here in section EE, and the depth of the cap beam was also 2 feet. And some of the bars had to be turned in order to fit everything in 2 feet, as you can see in the lower picture. So here is the cross-section of the column, 21-inch octagonal. The 6 number 8 bars are arranged in a circular fashion, which is the practice here at Utah DOT. The cap beam itself is 9 feet long. The column is 8 foot 6 inches. And at the very top of the column, at about 1 foot 6 inch depth, we made the column square so that we could grab it with our actuator and apply the lateral load at a point roughly equivalent to the mid-height of the column, where presumably the seismic moment there is 0, the point of inflection. So here you can see on this top figure the fastened grouted sleeve with the 2 ports, the inlet and the outlet, arranged in a circular fashion. And then you can barely see, perhaps up here, the place where the bars are fastened. You can see we provided the hoops for the 6 number 8 bars, as well as some exterior hoops for the sleeves themselves. The most important part of this picture, of course, is the template. You can see the octagonal template, which is very important for construction, because even though there is some tolerance in these sleeves, there needs to be a very good construction procedure so that all 6 bars will fit all 6 sleeves. On the other hand, in this lower picture, you can see the bars that come from the cap beam sticking out. They're usually made larger so that we can tie them easily, and then we cut them so that to prepare them for insertion in the sleeves themselves. Here is the second specimen, this number 2, where the sleeves now are inserted into the cap beam, and you can see the dimensions are identical. And also here in this picture you can see the sleeves inside the cap beam. And needless to say, I think you can imagine from this picture that there is significant congestion and it's very difficult to build. However, just as a reminder, this is a half-scale specimen, so there's bound to be some more congestion. In the lower picture, you can also see that these are going to be the bars that are inserted then into the cap beam. And again, I have to point out the wooden template, which is very important for proper construction. Finally, this category 1, you can see the monolithic specimen, the cast-in-place, as we call it. And here it's important to note that there is not even a lap splice here, let alone any mechanical splice. The bars are monolithic, bent, and they're going all the way to the top. So this is the perfect specimen, as you can see. So here we are in the construction sequence. You can see now in this particular one, the sleeves are inserted in the cap beam. So this would be number 2. And you can see this is a pre-grout operation. The grout is inserted first, and then the field dowels are inserted upside down, as I mentioned. And then you can see we have a little bed of grout here. And here is the final product. Temporary support is typically provided, which is not shown here, but the grout can get very high strengths in a matter of 3 days. We can get something like 7,000 psi compressive strength of the grout. So in preparation for testing, you can see here we've clamped down the cap beam or pier cap upside down. We've applied an axial load. The axial load is in the range of 6% of the capacity of the column in compression. And you can see the actuator in the horizontal direction attached to a load frame. And from what I'm going to be saying from now on, we can assume that the center line of the actuator is about 8 feet or 96 inches. So as we are pushing laterally to the left and to the right here in this type of motion to this side and to the other side, we are simulating the application of a horizontal load or displacement. Actually, this is a displacement control test which simulates how an earthquake would be affecting this bridge subassembly. So here I'm going to show you some instrumentation which was applied in the terms of electrical strain gauges to the bars themselves and to the hoops, and so we could know whether something has yielded or not. And in addition, we applied these linear variable differential transformers. They are really position sensors that measure very fine movements on the two sides of the columns. You can see here the load is applied in the east and west direction, as you can see up there, and the measurements are made also on the east and on the west face of the column. Just as a reminder, there is 8 bars, but 2 of the bars are along this line right here next to the instruments, and 1 there and 1 over here. And those bars, based on the way we're applying the load in the east and west direction, are going to see much of the stress and deformation. So we also instrumented the specimens up here on the top with these potentiometers. It's a very fine line. You cannot see it. It's a string potentiometer which measures fine movement of the specimen in the east and west direction. There's one here and one on the other side, and they are applied at the far ends of the specimen so that you can even detect any torsional misalignment. So in order to do the test, we're using a loading protocol that was developed by Committee ACI 374, which is the seismic design of buildings. And the reason is, in this displacement control history, we're applying 2 cycles per drift ratio. As you can see here, researchers found that if you apply 3, which was typically the norm, you're applying too many cycles and you're failing the specimen in low cycle fatigue. So the first cycle, as you can see here, was roughly half of the predicted yield displacement, something like half an inch. The second 2 cycles are the yield displacement, roughly 1 inch. Then twice that, 3 times 3 inches, 4 inches, 5, 6, 7, 8, 9, 10, until we fracture bars or until something catastrophic happens and the load capacity drops significantly. In the beginning, we were trying to make measurements and mark cracks and see what's spalling, what's cracking, and so we go slowly. So up to this cycle, first 6 cycles were carried out at a displacement rate of 1.2 inches per minute, as you can see here. And then after the 6 cycles, it's like watching grass grow, because for these large deformations, we go a little faster, 4 inches per minute. But both of these speeds are nowhere close to what an actual earthquake would do. That's why they're called quasi-static cyclic loads. Nevertheless, we believe they represent what a real earthquake does to our bridge. So here are some test results for the first specimen, the fastened grouted spliced sleeve. which as a reminder is the one where the sleeves are in the column in the plastic hinge region where damage is expected. And sure enough, you can see that in this particular hysteresis performance, which plots the force versus the drift ratio. Drift ratio is the horizontal displacement divided by the 8 feet, which is the height of the column, which is also similar to inches because 8 times 12 is 96. 196 is pretty close. So when we say 2%, is roughly 2 inches. So you can see at about that place we saw cracks and spalling both in the push and in the pull direction. And at about 6% drift ratio, we had pull-out failure. Actually, what happened is exactly what we saw in the sleeve test, where the connectors themselves showed us this. We had a grout cone, and the bars actually pulled out of the sleeve. Down below here, you see a graph of the normalized height above the cap beam top face versus the curvature. The curvature tells you more or less how the member is bending. So you can see that in this particular case, at the top of the sleeve, which is this line here, we see some stress, some curvature concentration, which implies that this particular connection did not perform as we expected. There is some discontinuity right above where the sleeve is, and this does not behave like a monolithic specimen. On the other hand, here you can see some pictures. At 3%, you can see cracking and spalling, as we said. This is when it happened. And then at 6%, you can see the bar pull out very clearly here for both this bar as well as this bar, which is exactly what we saw also in the sleeve test. And of course, at 6%, the specimen lost any lateral strength. So that's the end of the test. 6% drift. Now the second one, where we applied the fastened grouted spliced sleeves in the cap beam, again upside down, had a significantly different performance. So you can see cracks and spalling again at about 2%, but now we actually had a rebar fracture. This solid line here, this solid circle, represents fracture of the bar itself, which is very significant. And at the other end, at about close to 8% drift, at the end we had also bar pullout, which is the failure mode that we saw earlier for specimen 1. But now here down below you can see, well, first of all, we can see that the hysteresis loops are fuller. There's no pinching here in the middle. This has good energy absorption, which tells us that this specimen behaved better than the last one. Down here at the bottom, we again see a plot of the normalized height to normalized curvature. And now we're seeing a performance that we usually see in monolithic construction, where the curvature actually is very, very large. Down here as we come from the top to the bottom of the column, which is what we expect to see from monolithic connections. So I would say this is a desirable performance. And you can kind of see here the 3% we have the spalling, 7% we had the bar fracture on one end, and at the other end the bar pullout. So you can see a good formation of a plastic hinge, and incidentally not too many cracks in the pier cap or capping, which perform very well. So finally, no surprise at all, this is the CastInPlace. We expected the CastInPlace to be the best specimen, and sure enough, again slightly above 2%, let's say 3%, we see cracks and spalling. At about 6%, we start seeing yield penetration into the cap beam, and at about 9% in this case, we see fracture of the bars on the east and west side. And our curvature curve looks exactly how it's supposed to, pretty symmetric in push and pull. And you can see as we come down to the bottom of the column right here at this point, that is the maximum curvature, and that's what we expect to see. So comparing this curvature with the one of the test before, specimen 2, you can see they are very similar. But comparing to specimen 1, where the sleeves were in the column, you can see this is not similar at all. So this tells us that specimen 2 with the sleeves in the cap beam actually performed better and try to emulate the cast-in-place performance. Here are some pictures from the cast-in-place performance. Again, 3% drift, we have spalling, 6% we're starting to see yield penetration, and at 10% you can see we have the bar fracturing and also a little bit of buckling there for the bar buckling. So if we compare the performance, this is an envelope, what you're seeing in this graph of lateral force versus drift ratio. You can see the three different tests that we carried out. In blue is the first one with the sleeves in the column. In red is the second one with the sleeves in the cap beam or the pier cap, and the black one is the cast in place. And obviously what this graph is showing you, as well as the table, the blue one, the one where the sleeves were in the column, had the lowest lateral drift, 6%, but also the lowest displacement ductility, which is a measure of how well it's going to do in an earthquake, slightly below 5. The second specimen, where the sleeves are in the pier cap or cap beam, went to a drift of 7%, and its displacement ductility, meaning how much it can displace past the yield point, was 5.8, and the cast in place went to a drift ratio of 10% and a displacement ductility of 9.9. This is indicative then that the second specimen, the one with the sleeves in the cap beam, performed well, closer to the cast in place. In addition, we plot here cumulative energy. Cumulative energy is where you can see how much energy is dissipated during the test. And of course, the largest one is the cast in place. The second one is the one with the sleeves in the foot, in the pier cap, and the third one is the ones with the sleeves in the column. Same thing for the equivalent damping ratio. So one last thing here is how much drift is left after the test is completed, and this shows you on the vertical axis that we have quite a bit of residual drift, but this is true also of the cast in place, somewhere around 8% at the end of the test, as well as the one precast one with the sleeves in the pier cap and the sleeves in the column. And this residual drift is what the new technologies with the pre-tensioning and the shape memory alloys are trying to avoid. They would have the column come back to being completely vertical at the end of the earthquake. So as a conclusion for these category 1 specimens for the pier cap, definitely we saw desirable performance, very ductile performance with rebar fracture and displacement ductility of 9.9 for the cast in place. It had a very good hysteretic performance and energy dissipations and very well distributed flexural cracks. The one where the sleeves were in the column had a very small spall region. The one where the sleeves were in the cap beam had a similar damage to the cast in place, and there is no sleeves in the column in this one. Rebar fracture was the failure mode for the cast in place, and premature rebar fracture for one bar for the one where the sleeves were in the pier cap for the precast one, and excessive bone slip which led to pull-out failure primarily for the one where the sleeves were in the column. So in addition, the more ductile response was observed when the sleeves were in the cap beam, and the ductility there increased from 4.9 to 5.8. We saw different distribution of inelasticity as evidence from the curvature curves. And the one that emulated the casting place better was the one where the sleeves were in the cap beam. From the strain gauge data, we saw that both the field and the factory dowels yielded, but for that is when the sleeves were in the column. But when the sleeves were in the pier cap, the factory dowels did not yield at all, which means inside the pier cap we didn't have any yielding at all, which is good news. So finally, if we compare the displacement ductility of all these tests, these three tests, they all exceeded the minimum ductility of 3 per Caltrans seismic design criteria, and 5.8 is a good one. It exceeds 5 per AASHTO design guide specifications for single column bends. So now let's go to category 2. Category 2 is the one where we're studying the connection to the footing between column and footing, and in this particular case we're using the grouted splice sleeve. The one that we're talking about is the NMB splice sleeve, where both bars are grouted. In this case as well, we did connector tests, as you can see, but as you can already see, in this particular test we actually had bar fracture. So it's a monotonic tension load, and in this particular case we did six connector tests, and in every single one of them the bar fractured. And the strength that we got was about 1.69 of the yield strength on average, which certainly exceeds the 1.25 for type 1, but we also reached the ultimate strength of the bar, 100% of the ultimate strength, which is qualifying this for a type 2 splice for buildings. But again, in bridges, you're not allowed to use it in the plastic hinge region. Nevertheless, the news is good. As you can see from the table, in all cases, we got the maximum bar stress to exceed 100 KSI, and the maximum bar stress normalized to the yield strength exceeds at least 1.63. And in all cases, all the connectors, all the bars fracture. That was the failure mode. So we were expecting to see performance superior than the last connector. And so in this case, we built 4 half-scale specimens. As you can see here, GGS1 is the one where the splice sleeves, the grouted splice sleeves, are in the column. GGS2 is where they are in the footing. And then here we tried a little different thing. We went back and replicated GGS1, but with one exception. After we did all these tests, we realized that because of the strain penetration, we have concentrated plasticity down below into our footing. So what we did, we debonded those bars in the footing, as you can see here by these red markings, for a distance of 8 bar diameters, in which case this translates to 8 inches into the footing. Our footing was 3 feet wide in this case, and so it was a little bit wider, but we wanted to see if debonding these bars in the footing would actually change the behavior of GGS1. Finally, for comparison purposes, again, we did a cast-in-place specimen for our footing to column connection. So here you can see the dimensions. Again, the footing is 2 feet deep. It's only 6 foot wide, but it's 6 foot long, sorry, but 3 foot wide, as you can see here, with similar details as we showed earlier. Number 4 spires are 2.5 inches, also in the footing, with properly designed to AASHTO guide specifications. So you can see here the dimensions. Dimensions are very similar except for the width of the footing, which is 3 feet, and its length, which is 6 feet. 6 number 8 bars again on a 21-inch octagonal column. The bars are arranged in a circular fashion. Here you can see the picture, and you can certainly see again the template. This is a very important part of the construction sequence. And may I say here at this juncture that all these specimens were built by graduate students. MJ Ameli, who's here with me. The other student was Joel Parks from Idaho, who's still here. And the next student, and I know it has to do with some of the audience, Dylan Brown, who's actually from Montana. So we had an international cast of characters here, starting from Montana, Idaho, Utah, and everyone else here. So you can see here is the sleeves included in the column. These are the splice sleeves. Again, you can see the inlet and the outlet, but again, I have to point out that this has a template, and you've probably been seeing some strange bars going in and out of the column. These were just instrumentation threaded rods that we use to attach our instruments. Here is the second specimen, the GGSS2, where in this case the grouted spliced sleeves are in the footing. Again, this does not, I'm not going to say that this is an easy job, but it can be done by amateur students, may I say, and amateur professors, right? So here is the template, the very necessary template, and these are the threaded rods that I was talking about earlier, which we use to attach our instrumentation. Moving on, the third specimen is identical to GGSS1, the first one, with the exception that here at the top, very top of the footing, for 8 inches, we have the debonding, which was achieved with very high technology, just a few turns of duct tape, the all familiar duct tape, which debonds the steel from the concrete. And as you will see, this was very important to observe. Finally, you can see the monolithic cast-in-place construction, which was again very similar to the earlier tests with the capping. So here is the design and construction of this particular type specimens. Again, I'm showing the sleeves, the splice sleeves in the footing, and then you see the field dowels that are coming. Actually, I'm sorry, this gives it away. This particular grouted pocket, it says to me the inlet is in the column, so actually this is the grouting bed, and the field dowels are actually coming from the footing up, and the sleeves are inside the column here in this particular case. And you can kind of see again the wooden truss that holds it up, and here you can see where we applied actually. You can kind of see the grout inlet and outlet in this particular picture. So moving on, the same story here. The configuration is almost identical. You can see the axial load that was applied here with threaded rods. The protocol was very similar to what we did earlier on. The footing is clamped down with these very high strength threaded rods. And here is the test. Here is the result for the first test with the sleeves in the column. And again, you can see that we have cracking at about 3%. We do see quite a bit of yield penetration, though, in this particular one. And as far as the curvature, we see again, this is the top of the sleeve, and we see that disruption again, which is very particular when the sleeves are in the column, that we see a discontinuous pattern in that. You can see bars fractured, but at 8%. You can kind of see the ruptured bar right here. But again, the pattern of damage is very similar. 3% we have spalling, 6% you see the yield penetration into the footing, 8% we see rebar fracture. So definitely this performance is better than what we saw in the cap beam. And no bar pullout because the failure was due to fracture. The second one, where the grouted splice sleeve is in the footing, you can see there's quite a bit of good performance. Again, eventual failure is rebar fracture. But again, you can see that this particular one, the curvature emulates more the monolithic construction as we expect. As you go towards the top of the footing, we get very large curvatures. Results, again, rebar fracture was the failure mode. You can see it here at about 7% drift. The third one, where we innovated a little bit and added this debonding length into the field dowels in the footing at the top 8 inches there with the duct tape, shows that we actually made an improvement. We exceeded 8% drift for the first time, I believe, for precast specimens. The hysteresis loops are very good. We get very nice performance. Yes, because the sleeves are in the plastic hinge region, we get again this disruption in the curvature pattern. But I have to say that we did here get rebar fracture at very large drifts, 8% drift. If you stop and think about it, 8% drift is really a tremendous amount of drift. 8 inches in this particular case, close to. But not to be outdone, here is the cast-in-place specimen, which always we expect it to be the best one. And this indeed was the best one. It went to 10% drift. And again, here we saw the curvature emulating, I mean, this is the cast-in-place. But if we go back to the specimen number 2, where the sleeves are in the footing, you can see it kind of emulates, again, the cast-in-place performance. And again, in this cast-in-place, eventual failure was fracture of the bars. You can see the cracking, spalling, and then crashing yield penetration at 6, and then at 9% we see the bar fracture. So if we compare this particular set of tests, which are the tests of the column to footing connection, it becomes clear now, a little clearer picture, that the blue one, which is the sleeves, the grouted sleeves in the column, only achieve a ductility of 5.4. The red one, which is the sleeves in the footing, achieve a better ductility of 6.1. The green one is when the sleeves are in the column but with the debonded length of 8 inches at the top of the footing. This one actually went a little better, 6.8 ductility, as well as a drift ratio of 8%. And then the last one is the cast-in-place. We can't seem to beat the cast-in-place. That's a ductility of 8.9 and a large drift ratio of 9%. So that's the story here, which is also reflected in the cumulative energy, how much energy the systems can dissipate in an earthquake. Finally, as far as rotation, how much bone slip do we get down here at the bottom? We get more bone slip rotation when the sleeves seem to be in the column, because we see this particular opening at the interface between the column and the footing. And when the sleeves are in the footing, the red curve or the monolithic, we don't see quite as big as bone slipping. So conclusions here for the category 2 type specimens. We saw, as always, desirable performance with rebar fracture for the cast-in-place with displacement ductility close to 9. Very good hysteretic performance for the cast-in-place and energy dissipation and well-distributed flexural cracks, which is what we want to see. For the precast specimens 1 and 3, we saw localized damage and a smaller region of spalling with respect to the cast in place. Similar damage to the cast in place for the one where the sleeves are in the footing. But the rebar fracture was actually premature for the precast specimens. But also we saw rebar fracture in the cast in place. But the difference is that for the precast specimens, we have higher values of concentrated strain at the interface. And just as an educational item, rebar fracture occurs because of two things. You have high strains in a concentrated area, and you have a lot of cycles. So this is called low cycle fatigue. I mean, when I say a lot, I mean 20 to 24, but this is enough actually to cause low cycle fatigue, which many of you are familiar. If you take a paper clip and you bend it in reverse directions in cyclic motion, after a while that paper clip will fracture. The same thing is going on here in our column to cap beam or column to pier cap specimens. So this is going to happen whether you have a cast in place or whether you have a precast specimen, the difference being because of the higher concentration of strains in a localized area in the precast specimens, that tends to be happening a little earlier. And what I mean by a little earlier, of course, I'm talking about 7 or 8% versus 9% drift. It's not a whole lot, but it is noticeable, as you can see. Finally, as far as conclusions go, and I have a few more slides regarding recommendations. Yes, it was more ductile to have the grouted splice sleeve inside the footing. The ductility increased from 5.4 to 6.1. On the other hand, if you kept the grouted splice sleeve in the column, but you debonded for 8 bar diameters in the footing, we got a little better displacement ductility, 6.8 versus 6.1. Nevertheless, all the precast specimens were less than the cast in place. So we saw, again, as we saw for the column to pier cap or cap beam specimens, a different distribution of inelasticity when the sleeves are in the column. And when the sleeves are in the footing, we see similar inelasticity to the cast in place. From the strain gauge data, we saw that both the field and factory dowels yielded for the specimens with the sleeves in the column. But again, as we saw earlier, for the case where the sleeves were in the footing, we did not see any yielding in the footing at all. And by the way, both the footing and the cap beam were not damaged at all. They remained practically elastic, which is the intent of the code, of course. As well as the joint regions were in very good shape. So in this particular column to footing specimens, the displacement ductility of all the specimens exceeded the minimum of 3 and the 5 for the ash to seismic single column bends. So now some observations. These were flexurally dominant precast specimens connected by grouted sleeve connectors. So one of the things we saw that if you confine the connector zone very well, this is advantageous. So transverse reinforcement should be used to secure the grouted slice sleeve connectors. So what does that mean? It means that the spiral length for a splice, we found out 2 extra turns is enough to do this. The Lenton or fastened grouted sleeve was found promising, but only for moderate seismic zones, because in this case you have to account for limitation of displacement ductility. It seems that if we place the Lenton inside the cap beam, we would get a little better performance, but the downside of this is that the construction is a little bit more cumbersome. The grouted splice sleeves for the footing, which were the NMB sleeves in this case, this was promising even for high seismic zones. But again, as we saw, we have to somehow limit the displacement ductility in these particular connectors. And we saw more ductile performance if the grouted splice sleeves was in the column base and a debonded region inside the top of the footing. However, I have to say there is a fourth option here, which we did not test because of limitation of our funding, which would be, of course, to place the grouted splice sleeve in the footing and then debond the bars in the column. But we can't speak of this because we didn't do the test. So I guess a big question here is going to be, all right, this is all nice and good, but how do I design such a particular connection? So we have some recommendations here, and some of these have been transmitted to the Utah DOT, where we understand they have actually presented some preliminary specifications for precast columns. And the design, of course, is based on the AASHTO guide specifications and the cultural seismic design criteria. But what we are proposing here is to actually limit the ductility by using a predefined length of the plastic hinge. So taking you back now as my capacity as professor, how do we define the ductility? We talked about this a lot during this presentation. It's really the deformation of the column divided by the yield deformation of the column. So in some ways, the deformation of the column is made of two components: the yielding part, just what it takes to yield it, and then the plastic part, what it takes to move it from the yielding to the ultimate. Now the yielding part is shown here, is some function of the length of the column and the curvature at yield. And then the ultimate is made of the plastic component. This plastic component is where we see L sub P. L sub P is actually the length of the plastic hinge, is where most of the damage in the base of the column is seen. So as you can see here, if we want to limit the ductility, we need to limit the plastic deformation. And to limit the plastic deformation, we actually have to limit the length of the plastic hinge. Now, we're doing research, of course, to determine exactly how much should the length of this plastic hinge be. And see here in this graphic, you can see the curvature that I kept showing you. This is this solid line, but we typically idealize it with a linear part and a plastic part. So if you look for the cast in place, you can see this is the length of the plastic hinge in this case. But how much is it if we use a precast column? So for the precast column, we're showing the one with the sleeves in the column. You can see we got a little different type of curvature. And also we are finding that perhaps we should limit the length of this plastic hinge by limiting the length of the plastic hinge for let's say a column like this one with a footing to be less than the cast in place. We're also limiting its ductility. So this is really I think a recommendation that we've made to the Utah DOT, and my student MJ and I are working on this, trying to come up with exactly how to design these things for an actual bridge. And we're finding out this is a very key parameter. By limiting the length of the plastic hinge, perhaps you can design the precast columns in the same fashion that you use with AASHTO, but knowing that you will not get the high ductility that you get with AASHTO and STC of Caltrans, but perhaps you could live with that, and all you have to do for the design is to lower your expectations as far as ductility by reducing the length of this plastic hinge. So I want to thank a lot of people here because I didn't do this by myself. I'm just presenting it. MJ is sitting here with me. He did a lot of work. Joel Parks, of course, is still a PhD student here doing something else right now. He actually worked on this with MJ and did some retrofit or repair, actually, to be more exact, of such connections. Dylan Brown, he's the guy from Idaho. Dylan Brown is the guy from Montana. He did also his master's, and he finished his master's, and now he's somewhere in Wisconsin working for Michael Baker. I want to acknowledge my colleague here, Professor Larry Rivley, who has been instrumental throughout this research. And Mark Bryan, he's our technician. Without a good technician, you can't do anything. And as I mentioned, the financial support of these DOTs, as well as the Mountain-Plains Consortium. And also, I want to acknowledge NMB Splice, Live, and Erico for donating materials. And finally, I want to thank you for being a listening audience, I hope. And I'm happy to... oh, I see a question already. What was the compressive strength of the concrete in the footing and the columns? It was around 6,000 perhaps PSI on the day of testing, between 6 and 8,000 in that range, mainly because not all specimens can be tested during the same week. It took us a lot to be able to do these 8 tests. And as far as I know, what the next question is going to be, what was the compressive strength of the grout? These are very high strength grouts, the ones that go inside the sleeve. On the test day, something between 12,000 to 14,000 psi. So approximately double the strength of the concrete is what these grouts inside the sleeves can do. Let's see, any more questions here? Well, I hope that this particular webinar has shown you that actually these splice sleeve connectors can be used in construction, especially in your states and even in Utah. I already showed you where they used it. They used NMB splice sleeve in the FrontRunner train, where they put the sleeves inside the footing there. And as I mentioned, Joel and Dylan, along with MJ Ameli and myself, had developed already repair techniques for these particular connections. So after an earthquake or a big event like a windstorm, these things can be actually repaired. And that's another MPC report, which you can find actually on the website. And if you cannot find it, I'll be happy to send it to you, or perhaps send it to Tim, and Tim can forward it to everyone interested. I want to thank you again for our attention. I think, oh, how much time is saved from precast columns? Very good question. A lot of time. Actually, you know, a typical bridge, I would say, we're talking now days. MJ thinks 60%. I think more than that. I think really the reality is with these particular connectors, we saw appreciable strengths in 3 days. So in 3 days, we saw something like from, let's say, 7.5 to 10,000 psi. In 7 days, we saw something from 8 to 10,000 psi. So in 7 days, you could start putting the next step, which if it's your footing first, in 7 days you can put your pier caps, and 7 days from that, presumably you can start putting your girders. So we're talking now, maybe even 3 days. We don't even have to wait 7 days. So in 1 week, let's say, you could start putting girders, which are probably pre-stressed, right? or even steel, for those who prefer steel. Eye girders. So,
Okay, if there's no other questions, I want to thank you, Chris, for doing an outstanding job on your first webinar. With that, thank you all for attending.